For our last section in this chapter on applications of differentiation, 4.9, we're going to talk about antiderivatives. So just like the name implies, this is the reverse process of taking a derivative. And we'll see that this topic is going to lead us into the second branch of calculus, which is integral calculus. So far, everything we've been doing in this class has been in the branch differential calculus relating to the derivative. And now that we're going to reverse the derivative and do it backwards, this will lead us into integral calculus. Here's some examples of situations where taking an antiderivative could be helpful. So the first one says a physicist who knows the velocity of a particle might wish to know its position. This is the backwards problem that we've seen before with an object in motion, right? We saw before that if you start with s, the position, you can find the velocity by taking its derivative. Right? So velocity would be s prime. But in this case, we're doing that in reverse. Now we're starting with velocity, and we want to find the position. So we need to go backwards, right? We don't want to take the derivative of v, we need to take the antiderivative of v. The second example, an engineer who can measure the variable rate at which water is leaking from a tank wants to know the amount that leaked over a certain time period. So notice what they're starting with. What they know is a rate, which is a derivative. And they want to go backwards from the derivative to the actual amount. Okay, so again, you need an antiderivative to do that. Third one, a biologist who knows the rate at which a bacteria population is increasing might want to deduce what the size of the population will be at some future time. So again, the information they know at the beginning is a rate. It's a derivative of some function. And they want to go backwards to find the function itself. So in all cases, right, the problem is the derivative is known, and you want to go backwards to find the function that results in that known derivative. Now we'll present the formal definition of the antiderivative based on our previous discussion. So the idea is you're starting with some function we'll call little f, and the goal is to find some other function which we'll call capital F, whose, when you take the derivative of capital F, you get the function you started with, right? And here's one way to phrase it. If capital F is a function whose derivative is the function little f, then we call capital F an antiderivative of little f. And here we've written it out more formally. A function capital F is called an antiderivative of little f on an interval I if capital F prime equals little f. Again, over that same interval I. So let's take this example to help make more sense of that. So notice we're given a function little f equals 2x. And we're asked to find some antiderivatives. So there could be more than one, right? It just says an antiderivative, not the antiderivative. So think for a minute, and maybe even pause if you want to think a little longer, of a function that when you take its derivative, you get 2x. So think of the kind of functions we've seen before. And can you come up with a formula that when you compute the derivative of that formula, you get 2x? Okay, so the function that probably comes to mind, we'll call it capital F of x, would be x squared, right? Because when you apply the power rule to that, you bring the 2 down in front, reduce the power by 1, and you get 2 times x to the first power. And that's exactly what the function little f is, the function we started with. So that tells us the formula we found right here for capital F, this is an antiderivative of little f. But we want to see if we can find some more. Right? Can you think of another function that when you compute its derivative you would get 2x? Right? It seems like x squared might be the only thing that works, right? If you think about other functions like exponential functions or sine or cosine, logarithmic, rational, none of them really seem like they would even be close to working. So what we actually want to think about are variations on x squared. And the idea is that suppose we took x squared plus 1. So let's try as our second guess. We'll call this one number 1. Second guess, capital F of x equals x squared plus 1. Let's check that. Let's compute its derivative and see what we get. So because it's a sum, right, we go term by term. So the derivative of x squared is 2x, and then plus 0, right, because the derivative of a constant is 0. And we get 2x, which is the original function. So this one worked also. So this is another antiderivative of 2x. Right? We found two functions that both work. Right? Both of them have derivative 2x. So based on this, you could easily generate more, right? We could try a third one. F of x equals x squared plus, and then choose another constant, right? Maybe 8. This also works because its derivative is 2x plus 0, which is just 2x. So this example hopefully makes clear what we're talking about when we mean antiderivative. And we've seen an easy way to generate several antiderivatives, right? Start with the first one you find, and then if you just add any constant to it, that will give you another antiderivative. So based on what we just saw with our example, we can have this result as this theorem here. So again, you're starting with little f, and if you can find one antiderivative and call that capital F, then you can generate more antiderivatives just by taking the capital F of x and adding any constant to it. But what we're saying here is even stronger than that. We're saying not only can you get more this way, but you get all of them this way. So if you take f of x plus any possible constant, you now have an infinite list of antiderivatives, right? Because there's an infinite number of choices for that constant. That infinite list of functions is all of the antiderivatives of little f. There are no others. Okay, so that's an important thing to know because our goal is often to find all of them. And this theorem tells you how to find all of them. You start by finding one, call it capital F, and then just put plus c at the end and you've got all of them. So let's go back to the example we did on the last slide, f of x equals 2x. We found one antiderivative, we called it capital F of x equals x squared. Right? We found some others too, but that was one of them. So now to find the general, and again general means all of them, general antiderivative, all we do is we could say y equals x squared plus c. Right? We take the formula of the 1, which is x squared, and then add c. This represents all antiderivatives of the original little f of x, which had the formula 2x. Again, so that means this infinite list of functions contains every single antiderivative of 2x. There are no others other than the ones listed here. Now, if we wanted to show at least some of these on a graph, it could be informative to see what that looks like. I just didn't leave myself a lot of space. So let's try to put it right here. So let's take the first one, f of x equals x squared. Right, we all know that graph. And then if we choose c equal to 1, we'd have f of x equals x squared plus 1. It would shift that graph up 1 unit. And if we chose 2, it would be x squared plus 2. It would shift it up another unit. So basically I'm choosing different numbers for c and then graphing the resulting function. We could choose c to be, say, -1. So that would take the original parabola and shift it down 1 unit. And if we chose c to be -2, it would shift it down another unit. So the graphs of all these, I can't graph them all, right, because there's an infinite number of them. But you can see they're all just the same graph shifted vertically. Right? And there are even infinite number in between any of these, right? Because I didn't sketch the case where c was 0.1 or 0.2 or 0.999, right? So I just picked a few representatives to show the shapes of all of the curves that are the antiderivatives of little f. And we could call this a family of functions, right? Because they're related in some way. Their formulas are very similar. So they form a family of functions. In this example, we're asked to find the most general antiderivative of each function. So let's start with a. We need to find a function that when you take its derivative, you get sine x. So think about the possible kinds of functions, right? Something like x squared, there's no way that would work, or x cubed, or x to any power. There's no way you're going to get sine when you take the derivative. Right, so most likely it's going to be some kind of trig function. So think about the rules we've learned for the derivatives of the 6 trig functions. We know derivative of sine is cosine, right? That doesn't work because we want the derivative to be sine. We also know the derivative of cosine is negative sine. That's pretty close. So let's start with that observation. We know the derivative of cosine x equals negative sine x. So we're only off by a negative sign. So we need to adjust our function. Instead of using cosine, let's try negative cosine. Let's take the derivative of negative cosine. Okay, so we keep the negative sign, right, from here, keep that. And then we multiply by the derivative of cosine, which is negative sine. And then the two negatives become a plus, so this turns out to be sine. So this worked, right? We were trying to find a function that, so we get to choose this, right? We wanted to figure out what function to put in here such that when we took its derivative, we got sine. And this function worked. So this tells us this is the antiderivative of sine x. Okay. Now we want to write the most general, the general antiderivative of f of x equals sine x. And we've been calling it capital F of x for the antiderivative. So we found its negative cosine x is one antiderivative. And then to get the rest of them, we just put plus c on the end. This formula represents all antiderivatives of sine x. And you can check it, right, by taking the derivative of capital F, right? We're now reversing the process. So we're starting with what we claim is the antiderivative. We can prove it by taking its derivative, and if we get sine x, then we know we're right. Okay, so start with the derivative of negative cosine. So we have a negative sign, and then multiply by the derivative of cosine, which is negative sine, and then plus the derivative of c, which is, since c is constant, its derivative is 0, and we get, this simplifies to sine x, which is the original little f, so it did work. Okay, let's go to b. So we're trying to find a function whose derivative, right, the question is what to put in there, equals 1 over x. So you might remember a formula that says the derivative of the natural log function, ln of x, is equal to 1 over x. So that tells us this is an antiderivative of 1 over x. The problem with that derivative is natural log has a restricted domain. Right? You can only plug positive numbers into the log function. Okay, so we have capital F of x equals natural log x as an antiderivative, but it's only defined for x greater than 0. So we'd like to extend this to a function that's defined over a bigger interval. And so what I'm going to show is that the derivative of natural log absolute value of x is also equal to 1 over x. So this is also an antiderivative of 1 over x. And it has a bigger domain, right? Because you can now plug negative numbers in, right? Because of the absolute value sign, if you plug a negative in, the absolute value makes it positive, so then you can take log of that. The only number you can't plug in is 0, but now we can plug in more numbers, positive and negative. So first, I want to show you this argument, right? So let's now prove what I just claimed, that this statement, right? Derivative of natural log absolute value of x equals 1 over x. So because of being defined by an absolute value, we could consider cases. Case 1, x is positive. So in this case, the derivative of our function, natural log absolute value of x, since x is positive, we can just drop off the absolute value and it will be the same. And we've already seen that the derivative of natural log x is 1 over x. So that works for that case. Case 2 would be when x is negative. So let's again look at the derivative of natural log absolute value of x. Now since x is negative, if you want to drop the absolute value bar, you have to change the sign of x to make it positive. And you change the sign of a number by multiplying it by -1. So negative x is actually a positive number, even though it looks negative, right? Because x was negative to start with, putting the minus sign in front of it makes it positive. Now let's take this derivative. This is going to be a chain rule problem. We know the derivative of the natural log function is 1 over the inside part. And then the other chain rule factor, multiply by the derivative of the inside part. The derivative of negative x is -1. And then the two negatives cancel, you get 1 over x. So it worked in both cases. We showed the derivative of natural log absolute value of x is always equal to 1 over x. So now we have our one antiderivative that we like better than just plain natural log x. And then to write the general antiderivative, so our final answer for this one, is very simple, right? We take, we'll call it capital F of x equals, take the one that we found, natural log absolute value of x, and then just put plus c at the end. So this will be something we want to remember because we'll use this from now on. Anytime you're asked to find the antiderivative of 1 over x, it's really not good enough to say natural log x. It's much better to say natural log absolute value of x. And then, of course, the plus c, we always put that at the end to get the most general formula for the antiderivative. This is part C. We want to find the antiderivative of x to some power n. So n is any number except -1. So let's think about what we know that's related to this. So x to the n is a power function, and we know the power rule for taking derivatives of power functions. Right, the derivative of x to the n, the rule is you bring the power n down in front and reduce the power by 1. We want to now reverse this process to find antiderivatives. So let's take a couple of examples. So let's take the case where n is equal to 1. So f of x would be x to the first power. Let's find an antiderivative of this. So we want to think of a function, capital F, that when we take its derivative, we get x. So it's going to be some other power function, right? It's not going to, there's no way it could be like a trig function or exponential. It's going to be some kind of x to some power type of function. So when you take the derivative of a power function, it reduces the power by 1. So we want to put a function here so that when we reduce its power by 1, we get x to the first power. So that suggests we need 1 power higher. We need x squared. But x squared doesn't quite work, right? Because the derivative of x squared is 2x, and we don't want the 2. We just want plain x. So we have to adjust this to get rid of that extra factor of 2. So we need to divide it by 2. Now let's check. When we calculate capital F prime, we're hoping we get x. So we keep the division by 2, and then the derivative of x squared is 2x. The 2's cancel, we get x, so that worked. Okay, so we just found the antiderivative of f of x equals x is capital F of x equals x squared over 2. Let's try a second example. Okay, let's take n equal 2. So our little f, right, it's x to the n, so now it's x squared is what we're looking at. Let's see if we can find an antiderivative. So we'll call it capital F. Now, based on the example we did a minute ago, we need to increase the power by 1, so this needs to be x cubed. Now let's check. If we take the derivative here, using the power rule, we would get 3x squared. So the x squared is right, but we don't want that 3 out in front. So to fix it, we need to divide by 3. Now let's check. Let's find capital F prime. So we keep the division by 3, right? That's like multiplying by 1/3. We keep that constant. And then in the numerator, we take the derivative of x cubed, which is 3x squared. The 3's cancel. We get x squared, which is what we started with. That's correct. So we just found antiderivative of f of x equals x squared is capital F of x equals x cubed over 3. And of course, we could put plus c, but the main thing is now just find an antiderivative. So based on these two examples, here's one of them. Our other one was right here, antiderivative of little y equals x. Now let's generalize, see if we can find a formula for the antiderivative of f of x equals x to the n. So looking at the two examples we did, notice in both cases we took the given function and we raised the power by 1. Right, we went from first power to second power here. On this example, we went from second power to third degree, right? So we know we're going to have to increase this power by 1 degree. So it will become x to the n plus 1. But in both cases, we divided by a constant. So let's see what we did. So when we wrote it as x squared, we divided by 2. When we've used x cubed, we divided by 3. So whatever this new power is, right, the original power here was 2. The new power is 3. Whatever the new power is, you need to divide by that same number. So here the new power is n plus 1. We need to divide by the constant n plus 1. And then to make it most general, we put plus c, right? Because as soon as you find one antiderivative, to find all the others, you just need to put plus c at the end. So this is an important formula. We'll use it very often. Right, you put this red box around it. This is the rule. It's like the backwards power rule for taking antiderivatives, right? The regular power rule is for taking the derivative of a power function. That's the rule we learned a while back. This is the reverse process of that. Right? To find an antiderivative of x to the n, you raise the power by 1 and divide by the new power. Right? That does sound exactly like the reverse of what we did here. To take the derivative of x to the n, you multiply by the power, and then you decrease the power by 1. One last thing before we leave this example, notice we removed the case where n equals -1. And the reason for that, if n is -1, this function is x to the -1, which is the same as 1 over x. We already learned its antiderivative in part B. Also, if you tried to apply this rule to take the antiderivative of x to the -1, you would raise the power by 1, so the new power would be 0, and then you would divide by 0, which is undefined. So this rule would not work for the case where n equals -1, but we learn how to handle that case actually in part B of this example. Let's apply this backwards power rule for finding these antiderivatives. So starting with little f of x equals x to the 5th, that's a power function. So we're going to use the backwards power rule. Now the antiderivative, we've been naming the capital of the same letter of the original function. So capital F of x equals. So we increase the power by 1, it becomes x to the 6th, and then you divide by the new power, 6. And then that's one antiderivative, and then to find all of them, you just add plus c. And that's all there is to it. It's very simple. Now number 2, this doesn't look like a power function, but we're familiar with square roots, right? It helps to rewrite them as a power. So we can rewrite little g of x as x to the 1/2 power. Now it's clearly a power function. So the antiderivative, we'll use capital, this time g of x equals. So now we want to increase the power by 1. So we take 1/2, that's the original power, and add 1 to it. So 1/2 plus 2/2 gives you 3/2. And then you divide by the new power, so divide by 3/2. And then we put plus c. Now we could simplify to make this look a little better. Dividing by 3/2 is the same as multiplying by 2/3. So we have 2/3 x to the 3/2 plus c. And we're done with that one. The third one also is not in the form of a power function, but if we rewrite it using a negative exponent, we could write it as x to the -3. It's now a power function, right? X to a constant power. So the antiderivative we'll call capital H of x. We want to increase the power by 1. So negative 3 plus 1 is negative 2. That's the new power. And then you divide by the new power. And then to make it general, plus c. And we could rewrite this if we wanted. That first term could be rewritten as negative 1 over 2x squared. Right, we brought the x squared to the denominator with a positive exponent, and then we still have plus c. Okay, so this example illustrates something we saw already with taking derivatives, and that is certain functions that are not in the form of a power function. Sometimes they can be rewritten in the form of a power function. But this time, instead of using the power rule, we used the backwards power rule to find an antiderivative rather than a derivative. This table is a summary of many of our anti-differentiation formulas. Now the nice thing about this is we can get these very easily by taking the derivative formulas that we already know and just reversing them. So let's look through these, because we're going to be using all of these fairly regularly. Let's skip down here first. So on the left side we have the starting function, and on the right side is the antiderivative. So this is just the reverse of the law we learned earlier, that the derivative of natural log absolute value of x is 1 over x. So here it's framed in terms of antiderivatives, right? The antiderivative of 1 over x is natural log absolute value of x. And this is one we actually just did recently in an example. So the next one, the derivative rule is if we start with e to the x and we take its derivative, we get e to the x. It doesn't change, right? So if you're doing an antiderivative and you start with e to the x, its antiderivative is e to the x, right? Again, the antiderivative is the function that when you take its derivative, you get your starting function. Now the next one, it's saying the antiderivative of b to the x is b to the x divided by natural log b. This comes from the rule we learned about the derivative of b to the x. If you remember that rule, the derivative of b to the x is itself times natural log of b. So by dividing out that extra factor of natural log b, think about what happens when you take the derivative of this function. Natural log b is just a constant, so we carry that along. And then the derivative in the numerator is b to the x times natural log b. The natural log b's cancel, and we're left with b to the x. The next rule, it says the antiderivative of cosine is sine. And that comes from the derivative rule. We know that the derivative of sine is cosine. We've just reversed it. Similar up here, the antiderivative of sine is negative cosine. This comes from the rule that we've learned that says the derivative of cosine is negative sine. So put another negative here. The derivative of this expression here, negative cosine, will be negative times negative sine, which is sine. This rule is starting from the derivative of tangent we know to be secant squared. So in this context, we're saying the antiderivative of secant squared is tangent. The next one comes from the derivative rule. Derivative of secant is secant times tangent. We just reverse that. And then all of these are just the reverse of derivative rules, right? We learned the derivative of inverse sine is 1 over the square root of 1 minus x squared, so we've reversed that in terms of antiderivatives. We learned the derivative of inverse tangent is this, we've reversed that. We learned the derivative of hyperbolic sine is hyperbolic cosine, and the derivative of hyperbolic cosine is hyperbolic sine. Okay, so this table just took a lot of the familiar derivative rules that we've learned and reframed them in terms of antiderivatives. Now let's go back to these top three. The antiderivative of x to the n, where n is any number except -1. We just derived this in an example in this lesson, and we found the backwards power rule, right? You raise the power by 1 and you divide by the new power. Now this rule says if you want to take the antiderivative of f plus g, you take the antiderivative of little f plus the antiderivative of little g. What this rule is telling us is that if you have a sum, you can take the antiderivative of each term individually. Now why do you think you can do that? Well, we know you can do that with a derivative, right? We learned a while back that the derivative of a sum, you can just go term by term over the sum and take the derivative of each term individually. Since this is just the reversed process of taking a derivative, it makes sense that the same rule would hold. And then the top one, if you want to take the antiderivative of a constant times a function, this says the antiderivative is just carry along the constant and then take the antiderivative of the function f. We had the same rule with derivatives, right? If you have a constant times a function, when you take the derivative, you just carry along that constant. So it makes sense that doing an antiderivative, the same rule would hold. So you'll want to spend a little time with this table and just realize that this is pretty much the reverse of laws we've already learned, formulas we've learned, so that it's not really a lot of new to learn, it's just reframing it so that you can apply these rules backwards when you're finding antiderivatives. Let's find these antiderivatives in this example. So the first function, we've got a sum or difference of 4 terms. So one of the rules we just learned is that when you're taking an antiderivative and you have a sum or difference, you can just take the antiderivative of each term individually and just keep adding. So we'll just go one at a time. So let's start with the first one. This is a constant times a function. One of the rules we just saw was that in the case you have a constant times a function, you just carry along the constant and then take the antiderivative of the function. Okay, so we'll call our antiderivative capital F of x. We carry along the 2. Now the antiderivative of x squared. That's a power function, so we just use the backwards power rule. We increase the power by 1, divide by the new power. So that's x cubed over 3. So that finishes the first term. Now we go to the next one. Notice we have 5 as a constant, and the 5 is being multiplied by 1 over x. So this is another instance of a constant times a function. So you can pull the constant out in front and just carry it along. Now we want the antiderivative of 1 over x. This was on the table on the previous slide, and we saw that antiderivative is natural log absolute value of x. Going to the next one, 2 to the x. That's an exponential function, right? It's not a power function. This one over here is a power function when you have your variable in the base and a constant power. This is the reverse. The variable's in the power, it's a constant base. So for an exponential function, that's on our table as b to the x. We saw the antiderivative is itself divided by natural log of the base, and the base on this one is 2. So 2 to the x divided by natural log 2. Now the plus 7, that's a constant. Right, so we didn't really talk about this one specifically, but you could view 7 as, well, let's just think of it this way. What function when you take its derivative, gives you 7. Right? If you think about what we've seen for derivatives, that would be 7 times x. Right? The derivative of a constant times x is just that constant. And that takes us to our last term, right? So we're done here. But we're asked to find the general antiderivative. We just found one antiderivative. But it's very easy to make it general. We already learned this. You just put plus c on the end and it becomes the general antiderivative. So that finishes number 1. Now looking at number 2, we have a quotient. Just like with derivatives, right? If you have a quotient, you can't just take the derivative term by term. It does not work for products and quotients. So the mistake here would just be to go through each term individually and take its antiderivative. So we haven't learned any methods yet for dealing with quotients for finding antiderivatives. The only thing we could try at this point is try to rewrite this so it's no longer in the form of this kind of quotient. And the obvious way to rewrite this, right, we know the rule that if you have a sum or difference in the numerator, you can split it up into separate fractions. So we'll have x cubed over x minus 4x over x plus 3 over x. And then that can be simplified a little bit. The first term simplifies to x squared. And then we've got minus 4 plus 3 over x. So now it's no longer a quotient, right? You might think the 3 over x is a quotient, but because the numerator is a constant, right, that's not really the same kind of quotient of two functions of x. Okay, so now we're ready to find our antiderivative, which we'll call capital G of x. And because we have a sum and difference here, we can just go term by term. We'll do 3 separate antiderivatives. So starting with x squared, that's a power function, so we use the backwards power rule, x cubed over 3. And then we have this constant. We just saw that in number 1, right? If you have a constant, the antiderivative is that same constant times x. Now the next one, we've got plus 3. You could view it as 3 times 1 over x. So carry along the constant 3. And then the antiderivative of 1 over x, we saw that one in number 1 also. It's natural log absolute value of x. And then to make this general, we put plus c at the end. Let's continue on to number 3, finding the antiderivative of this function, which we'll call capital H of t. So first we've got a constant 4 times a function. So we carry along the constant. Now we need the antiderivative of cosine. So this was on our table, right? And it came from the fact that we knew the derivative of sine is cosine. And so in reverse, that tells us the antiderivative of cosine is sine. Then we carry along on the, so let me mention first, we have a difference here, so we can go term by term, find each antiderivative individually. Now we're on this one. There's a constant multiplied by a function. We carry along the constant. Now we need the antiderivative of sine. So this was on our table we just saw, and it's negative cosine. Right, so you have to remember that negative sign. And it's because the derivative of cosine is negative sine. So there's an extra factor of the negative that also appears in the antiderivative rule. And then we need to put plus c to make it general. And if you wanted to simplify, we could write it as 4 sine t plus 3 cosine t plus a constant. Now the last one, if you don't think about that being a familiar formula, you might not know what to do with this. But this is actually on our table, especially if you pull the 5 out in front. That leaves multiplied by 1 over 1 plus t squared. That expression, 1 over 1 plus t squared, appeared on our table, although we had x in place of t. And the antiderivative of that is the inverse tangent function. So there's not a lot of work on this one, our antiderivative, capital F of t. We carry along the 5, and then the antiderivative of that expression in parentheses is just inverse tangent of t, right? We have to use t instead of x because it's in terms of t here. And then, of course, just like all of them, to make it general, we add a constant. This example, we're asked to find a function f given this information. So we're given a formula for f prime of x, and then we're given some extra information that f of 0 equals 2. So notice they've given us the derivative of f, and they're asking us to find f itself. So we need to undo the derivative, right? We know the formula for f prime. We need to undo the derivative to get backwards to f. In other words, we need to take an antiderivative of f. So the first thing we observe is little f is an antiderivative of f prime, which is this formula here. Notice I said an antiderivative. We've seen that there's always, if there's one antiderivative, there's always an infinite number more by adding plus c. Now, how are we going to choose which one? Well, this condition will help us determine which antiderivative. In other words, what constant to use where we have plus c. So we're going to use this to help pick the correct antiderivative. So before we solve this, I just want to mention that the equation we were given here for f prime, this is an example of a differential equation. A differential equation means you have an equation, so you have an equal sign, and somewhere in the equation there's a derivative. And notice here we see f prime, there's our derivative. This condition to the right is often part of a differential equations problem, and it's called an initial condition. So I just wanted to mention that because one of the sequences after, or one of the courses you take after calculus is differential equations, and this is an example of the type of problem you'll see in that class. Okay, so back to our problem. We need to find, let's start by finding the general antiderivative of the given formula. So this is the same as the last example we were just doing, right? So we'll call it capital, actually we don't want to call it capital F. Now let me explain why. In the previous example we started with what we call little f, and whatever its antiderivative is we would call capital F. Here we're starting with f prime. When we undo the derivative, that will turn it into just f, the same function without the prime. Okay, so we're going to call the antiderivative little f of x. Now look at what we have in our formula. We have a sum of 3 terms, so we know we can find the antiderivative of each term one by one. So starting with the first one, we carry along any constant that's being multiplied. And then we need the antiderivative of e to the x. Well, that's an easy one. It's just e to the x. Then we've got minus. Now here, the dividing by 2 is just like multiplying by 1/2. So we could view this as minus 1/2 times x. The minus 1/2 is a constant. We just carry that along. And then we need the antiderivative of x. Well, x is like x to the first power, a power function. So we raise the power by 1, make it the second power, and then divide by the new power. That finishes the second term. We go to the next one, 4, right? We've seen this one before. The antiderivative of any constant is just that constant times your variable, which is x in this problem. And then to make it general, we put plus c. That's the general antiderivative. So we have here an infinite number of formulas here, and all of them satisfy that if you calculate the derivative, you would get this formula here. And you can even check that if you want, just to convince yourself that it would work. But there's this other condition. We want to choose out of all of these functions here, we want to choose which one, or maybe more than one, satisfies this condition, that when you plug 0 in for x, the output is 2. So we're going to use that now, that condition, to help us pick what value to use for c. Right, because not every c is going to make the function work so that it satisfies that initial condition. So what we're going to do in order to use this is plug in the numbers. Notice here 0 is an x value, right, because it's f of x. So 0 goes in for x, 2 goes in for the function value, which is over here. It's like the y, right? So we're going to sub in to our function for f, which is right there. X equals 0, and then f of 0, which is y, equals 2. Okay, so let's do that now. On the left, when we plug in 0 for x, this will be f of 0, but f of 0 gets replaced with 2. So the left side is 2. On the right, we have 3 times e to the 0 minus 1/2 times 0 plus 4 times 0 plus c. Now simplify this. E to the 0 is 1, right? Any number to the 0 is always 1. So that's 3 times 1. The next two terms are both 0, so we can just drop those out, and then plus c. So notice we have 2 equals 3 plus c. Solving that for c, we get -1. Now we know the correct value for c to use in the function. We need to make sure, though, that we write the final answer clearly. In this problem, we were asked to find f, not find c, right? So you don't want to stop here where we said c is -1. They asked us to find f. Well, we were part way there right here when we found the general antiderivative. But this one, the problem was it didn't satisfy the initial condition necessarily. We had to narrow down out of this list of infinite number of functions. We had to pick which one of them will satisfy the condition f of 0 equals 2. And what we found down here is that if we sub in -1 for c and write out that formula, that's the one that works. So our final solution, we'll write it out clearly. F of x equals, now I'm going to copy the formula for the general antiderivative, 3e to the x. This next term I could write as minus x squared over 4, and then plus 4x. Now here's the plus c, we're going to replace it with -1. And now we have our answer. Okay, so we're claiming this formula satisfies the given information. If you were to take the derivative of this formula, you should get exactly what we see here. And that's very easy to check, right? Derivative of 3e to the x is 3e to the x. That part matches. Here you'd bring the 2 down in front. The 2 over 4 simplifies to 1/2, and you reduce the power to 1. So minus 1/2 x. That matches here. Derivative of 4x is 4. That matches here. Derivative of -1 is 0. So clearly the derivative worked. When we took the derivative of our formula at the bottom, we got the given formula. Then we can check to make sure f of 0 equals 2. So just plug 0 into this formula, see what you get. Hopefully you get 2. E to the 0 is 1, so this first term is 3. Minus 0 plus 0, minus 1. So altogether, 3 minus 1 is 2, and it worked also. Okay, so this is introducing you to a few of the basic ideas of differential equations, but it's also within this topic of calculus. Let's read through this example. A ball is thrown vertically upward with initial speed 48 feet per second from the edge of a cliff which is 432 feet above the ground. We're asked to do several things. First, find its height above the ground t seconds later. In other words, find a function for its height. That's a function of time. Then we have a few questions. When does it reach its maximum height? When does it hit the ground? And what is its speed when it hits the ground? I'm going to start by making a sketch. We have vertical motion. So this axis represents the motion. It's the line that the ball is traveling along. We need to start to determine where to put 0. We could put it at the ground or the cliff level where the ball starts. Those are the obvious choices. And in some cases you might choose one, some cases you might choose the other. Now here they asked us to find its height above ground, so that makes sense to put 0 at the ground level for this problem. Okay, so here's the ground. We're going to put 0 right there. And then you also need to choose which is the positive direction, up or down. And you can choose either way, right? We're used to choosing up for positive. But if I had chosen to put 0 where the cliff is, then I could choose the positive direction to be down. It would be perfectly fine. It might even work better in that case. But because I put 0 at ground level, we're never going to look at below ground, right? So I'm going to choose the positive direction to be up. So the cliff is 432 feet above ground. So here's 432 feet. This is where the cliff edge is. And that's where the ball starts. So the ball will start here, and it's thrown vertically upward. At some point it'll reach its maximum height, and it will start falling, and it will fall till it hits the ground. Now there won't be an arc like this, right? I just showed that so you could see the upward followed by downward motion. It will be all in one vertical line. Okay, so that's a picture we can use. Now, let's start thinking about how we're going to approach this. This is a free fall problem, right? Because it's just vertical motion. And so gravity is the force that's acting here. So what we know is on Earth, right, if we're close to the surface of Earth, we have acceleration due to gravity. And we normally call that g, right? So we know the acceleration, which we could call our acceleration function a of t, would equal g. Now we need to think about the sign, though. Is acceleration due to gravity acting in the positive or negative direction? Well, we know it's acting down towards the Earth, but then you have to think about, is the downward direction, based on our choice here of the positive direction being upward, anything that's acting down would be a negative. So the acceleration here is actually negative g. Now g, we often think of that as the 9.8, but that's in metric units. Notice in the problem, measurements were in feet. If those were in meters, I would use metric units, so I would choose 9.8 for g. But since we're using feet, right, British units, we need to use g as 32 feet per second squared. Okay, so now this is negative 32, and if you wanted, you could put the units on it of feet per second squared. So notice what we know is the acceleration. Right, we know a of t is negative 32, and we want to find position, which we usually call s of t. Think about the relationship between those two, right? What else do we know? That if you start with s and you take its derivative, that gives you velocity. And then if you take a second derivative, that gives you acceleration. So acceleration is the second derivative of position. We know the acceleration, which is s double prime, right? So we know, we could write it this way, we know s double prime is negative 32. We want to go backwards to find s, so we're going to have to take two antiderivatives, or take the antiderivative twice, right? All right, so now we have a general strategy. This is similar to the example we just did, right, where we were given f prime and we wanted to find f. In order to complete that problem, we also needed an initial condition. So let's look at our problem and see if we have something similar to an initial condition. So that would be like, initial means at the beginning, and here at the beginning is time 0. So what did they tell us about what's happening at the beginning? So it says there's an initial speed of 48 feet per second. Velocity is like speed, right? So the initial velocity, in other words, the velocity at time 0 is 48 feet per second. But we need to be careful about the sign. Should that be positive or negative? Notice that the ball was initially thrown upward. That's the positive direction. So that should be positive 48 feet per second for the velocity. Now there's another initial condition given, and that's for the initial position, right? We were told the position of the ball when it was thrown. Okay, so that condition, s is position, then we plug in time 0, so that means the position at time 0 is, and we can see from our picture, right, it's 432. That's the location of the top of the cliff. So now we have basically what we're starting with, and we know what we need to do, right? We've got s double prime, that's acceleration. We need to take an antiderivative, that'll give us velocity, and then we take an antiderivative of velocity, that will give us position. Every time we take a derivative, we're going to add a constant, right, that plus c, and these initial conditions can be used to pick out the correct value for that c, just like we did in the last example. I've summarized what we found on the previous slide. We have our acceleration function, and then we have our initial velocity and initial position. Okay, so we've already discussed that we need to take an antiderivative of the acceleration function. Okay, and that will give us velocity, right? Because the derivative of velocity is acceleration. That tells us the antiderivative of acceleration is velocity. Looking at the acceleration function, it's just a constant, negative 32. So the antiderivative is that same constant times your variable, which is t, and then always remember to make it general, plus c. Before we take our next antiderivative, we need to figure out what number we should be using for the c. So we're going to use, because this is a velocity function, we're going to use our initial velocity, v of 0 equals 48. to find the correct value for c. This is just like we did in the previous example. So we're going to sub in the 0 is a t value, and the 48 is the v value, the v of 0. So over in our velocity equation, we're going to replace this left side, that's our v of 0, will be replaced with 48, and the t will be replaced with 0. So that gives us 48 equals 0 plus c. Whatever you get here, then you would then solve for c. We get 48. And then we can rewrite our velocity function. Just copy it, but replace c with 48. So v of t is negative 32t plus 48. Okay, so that's the first step. That was one of our antiderivatives. We're trying to get to position, so now we need to take an antiderivative of the velocity function, and that will give us position. That'll be our s of t. And again, the reasoning for that, we learned earlier that the derivative of s gives you velocity. That means the antiderivative of velocity is s. So look at your formula for velocity, take an antiderivative. Here we have a constant times t, so we carry along the constant. And then the antiderivative of t, using the power rule backwards, is t squared over 2. Then we have plus 48, which is a constant. So the antiderivative is 48t. And then make it general by putting plus c. We could simplify. The first term is negative 16t squared, and then the rest is the same. Again, we have a plus c. We always use an initial condition, if we have it, to find the correct value for the c. Okay, this function is s of t. It's a position function. So we need to use the initial position, which was s of 0 equals 432, to find the value of c. So the numbers we're substituting in this time, 0 for t, 432 for s of 0. The s of 0 is on the left. That'll be 432. And on the right, wherever you see a t, plug in 0. So when we do that, we have 432 on the left. Then we have negative 16 times 0 plus 48 times 0 plus c. Easy to solve this equation for c. We get 432. Okay, so now we rewrite our position function, but sub in the value we just found for c. So let's use the simplified version of s, which is over here. So copied the first part. Negative 16t squared plus 48t. Now plug in 432 for c. So this was one of the things we were asked to find in the problem, was the position as a function of time. So we have that. But then we had several questions. So we'll address those questions on our next slide. We can use the results we found to answer these questions. So first of all, when does it reach its maximum height? Let's think about what we know when it reaches its maximum height. So here was our picture. The ball started here at the top of a cliff. It went upward. Here's its maximum height, and then it starts falling. We don't know what its position is at the maximum height. Do we know anything about its velocity? Well, yes, at that point, right as it goes up, it gets slower and slower and slower until it reaches a speed of 0 at that instant, and then it starts falling. So we do know the velocity is 0 at the instant when it reaches its maximum height. So what we can do is take the velocity function that we found on the previous slide and plug in 0 for the velocity and solve it for t. Okay, so that gives us 0 equals negative 32t plus 48. We're solving for t, so we get 32t equals 48. And then finally, t equals 48 over 32. And that simplifies to 3/2, or 1.5. And then we need to put units on the problem. So this is a t value for time. If you remember the units we were using for other terms here, we had things like feet per second squared, right? Our acceleration was in feet per second squared, so time is being measured in seconds. So it reaches its maximum height 1.5 seconds after it was thrown. Now they didn't ask for this, but they could have asked, what is the maximum height? How high does it go before it starts to fall downward? That would be easy to find because we now know the time that it reaches that maximum height, and we have this position function. It tells you remember s here is the height above ground at any time t. So you could just take this t value, plug it in here, and find the position. Okay, they didn't ask for that, so won't write it out, but if they did, that's how you would answer it. Next question, when does it hit the ground? Okay, so in our picture, the ball went up, started falling, hits the ground. This is what we're interested in. Well, you might think, well, the velocity is zero there also. So set v equal to 0. But the velocity is only 0 because it hit the ground, right? It had a really fast velocity right at the instant it hit, and it just suddenly stopped because of the ground being there. So it's not really correct to say the velocity is 0 when it hits the ground. Notice the next question, what is its speed when it hits the ground? They're even asking us, what is that speed? So we don't know the velocity here, but we do know the position, right? When it's on the ground, the position is 0 because s represents the height above ground. So we're just going to plug 0 in for s. So look at the formula for s up at the top right. We'll replace the s of t with 0, and on the right, just copy it. And we want to solve this equation for t. It's a quadratic, so we know we could solve it. It might make it a little bit easier to solve if we divide by -16. That'll cancel out the coefficient in front of t squared. So when we do that, we'll get 0 over -16 is still 0. And then on the right, we'll have t squared. Now 48 over -16 is -3, so that's -3t. And then 432 over -16 simplifies to -27. And then you could try to factor it, but it doesn't factor easily. So let's use the quadratic formula to solve this, since it's a quadratic equation. So in the numerator, we take negative b, so -3 plus or minus the square root, b squared, so -3 squared, minus 4 times a times c. A is 1, c is -27. All over 2 times a. A is 1. Now let's simplify. So we'll have in the numerator +3 plus or minus the square root of, so that's going to be 9 plus 108. So that altogether comes to 117 under the square root. And then it's all over 2. Now 117 is actually 9 times 13. And since 9 is a perfect square, you can pull out the 9 as the square root of 9, which is 3. Okay, so in the numerator we keep this 3 plus or minus. We pulled out the square root of 9 as a 3, and then we still have 13 under the square root. Okay, now if you put these in your calculator, you'll have two answers, right? One with a plus, one with a minus. So those come to, when you use the minus, it rounds to about negative 3.9, and when you use the plus, it rounds to 6.9. Now the negative 3.9 doesn't make sense, right? Because it started at time 0 and we went forward in time. So we can throw that one out. And so the 6.9 has to be the right answer. So our answer is it hits the ground 6.9 seconds after being thrown. Okay, now the last question, what is its speed when it hits the ground? Speed is given by the velocity function. So we're going to go back to our velocity function and plug in the time when it hits the ground, and that's what we just found. So we're going to plug in 6.9 for t. Now the velocity function is up at the top of the slide, so it's negative 32 times, plug in 6.9 for t, plus 48, and then calculate what you get. Negative 172.8. Now why is it negative? Remember, velocity, the sign means something, unlike speed. Speed is always positive. The sign tells you about the direction. So we decided the positive direction was up. So velocity being negative means that it's moving in the downward direction. So the speed is 172.8. The minus just tells us it's acting downward, but we already knew that from the context. The object is falling when it hits the ground, falling downward. So our answer for the speed would just be 172.8, and make sure to put units on it. Right? Acceleration was feet per second squared, right? So speed would be feet per second. Okay, so that's how fast the ball was falling at the instant it hit the ground, right before it came to a stop. So basically in this problem, we first did the new calculations, which was taking antiderivatives, plugging in initial conditions to go from our acceleration function to finally to get to our position function. But then you can answer various questions. These are samples of types of questions you can answer from the work you already did. Right, so these questions are not calculus. These are questions you could have answered before calculus. But we're just showing some of the applications of the results we got from calculus. Now we're looking at an example where we're given the graph of a function and we want to sketch a graph of its antiderivative. We did this type of problem in the other direction already, right? Earlier we had problems where I gave you the graph of a function and then based on that we would sketch a graph of its derivative. Now we're working backwards. So if you remember the method we used last time, so if we were presented with this graph here and you wanted to sketch its derivative, what we would do is pick various points on this curve, sketch the tangent line, and estimate the slope of the tangent line, and that would tell you the y-coordinate to plot on the derivative function. So for example, if we picked this point here corresponding to x value 2, you can see the horizontal tangent, meaning slope 0. So over at x-coordinate 2, we would put a y value of 0. And say if we picked x-coordinate 3, it's clearly a negative slope. We might estimate that at some number, say negative 1. So over here at x value 3, we would put a y value of negative 1. So now we want to do that backwards. So for example, this point has y-coordinate 0. Over here, we're now thinking of this as the y-coordinate as representing the slope. So the slope is 0. So when we sketch our curve over here, we want it to level off like a mountain peak or a valley bottom, so the tangent would be horizontal and have slope 0. Same thing at x-coordinate 3. The y-coordinate here is 0. So over here at x-coordinate 3, we need our curve to level off and have a horizontal tangent. So let's start making some notes here. We want the slope to be 0, okay, at that point. Same thing at 3. The slope should be 0 for the antiderivative. So to give us some notes on our actual graph, at x-coordinate 1, I want to sketch something that has, it could be either a max or a min. It's going to have a horizontal tangent. And I put that right over x value 1. And then the same thing at x value 3. We want it to have a horizontal tangent. Now let's think about the other points. So in between those 2 points, the y-coordinates are positive. That means the slopes for the new graph will be positive. Okay, so let me label that part. This whole region here has positive slope. So between, what I could do is make a number line down here. We already said at points 1 and 3, the slope will be 0. And in between, the slope will be positive. Now let's look to the left of 1. Over here, we're not making tangent lines here, we're just looking at the y values. The y values are negative. That means the slopes on our new graph will be negative on that region to the left of 1. Okay, so over here to the left of 1, I'm going to put slopes are negative. And then all that's left is to the right of 3. Notice these y values are negative. Doesn't matter that shape of that curve. All that we're looking at right now are that these are negative y values. Okay, so slopes are negative. So over on the right, to the right of 3, we have negative slopes. Okay, now if we want to start visualizing the curve, negative slope means decreasing. Positive slope means increasing. So we can start visualizing our curve. Decreasing till we get to 1, switches to increasing. When we get to 3, it starts decreasing. Now there's one other piece of information we need to include. F of 0 equals 2, so I might want to label some points on my axes here. Okay, so we have the point right here. We know our graph passes through that point. Okay, so let's start making our graph. It needs to start out, you can look at the number line we made below, starts out decreasing until we get to x-coordinate 1. We don't really know how steep it is, it's just decreasing. Then it switches to increasing, and it increases until we get to an x value of 3. So when I get vertically above the 3, I need to switch it from increasing to decreasing. And then it stays decreasing the rest of the time. But now before I sketch the rest of it, let's just point out a few things. Notice here, slope 0, which is what we said. We didn't know if it was a max or min at that point, but it has to have a horizontal tangent to correspond to this point here having y value 0, meaning slope 0. Same thing at x-coordinate 3, you should have a horizontal tangent. Now let's think about what this shape tells us. So far we only use the fact that it's all negative to tell us negative slopes and decreasing. But does this give us any more information, the fact that it curves down and then back up? So when we start off moving to the right of 3, the y values are getting farther from 0, right? Maybe -1, -2, -3, which means steeper, but in negative slopes, but steeper. And then once we pass x-coordinate 4, the y values start to get closer to 0, and they're eventually approaching 0 like an asymptote. So something happened at 4, right? So to the left of 4, it's getting steeper. Still negative slopes. And then to the right of 4, the slopes approach 0. So let's see if we can make that appear on our curve to the right. So as I continue down here, I want the slope, I want it to get steeper. Okay, so it's going down pretty quickly. But then once we hit 4, the slopes start going to 0, meaning the tangent lines start getting closer to being horizontal. So the curve has to be leveling off. It has to stay decreasing this whole time, but it's going to start out getting steeper and steeper all the time. And then when we get to 4, it's going to start leveling off. Okay, so here we come around here, it's getting steeper, steeper. Here I'm directly above the 4. Now I'm changing the concavity because it's going to start leveling off. It doesn't mean the y values are approaching 0, right? That's not necessarily the case that this is a horizontal asymptote. It could have a horizontal asymptote somewhere else, up higher or down lower. The point is, it's leveling off. It's becoming more flat as we go to the right. So this is our guess as to a graph of this antiderivative, which we're calling capital F of x. Okay, and it's just an estimate. We didn't know enough about it to get it exactly correct. For example, we didn't know how far down this should go before it turns around, switches from decreasing to increasing. We don't know where that happened. Maybe it came way down here before it turned around. Same thing with this other maximum point when it switched from increasing to decreasing. Okay, but it does give us a general idea about the graph of the antiderivative. So today we covered all of section 4.9, which is on antiderivatives. First we defined what an antiderivative is, and then the concept of a general antiderivative. So the main idea here is the general antiderivative is a formula that represents every single antiderivative to a given function. So we also found the way to find it is you start by finding one antiderivative and then just add a constant, put plus c at the end, and now you have the formula of the general antiderivative. Then we presented a table of antiderivatives. So we didn't have new formulas to learn. We just took the formulas we already know for derivatives, and we reversed those rules to derive these new formulas for antiderivatives. Then we looked at some examples that fall in the category of differential equations with initial conditions. So this is the type of problem where you're given either f prime or f double prime, for example, and you want to work your way backwards to get to f. So if you're given f prime and you want to find f, you need to take an antiderivative of f. And then the initial condition is always a way to help you find the correct value for the c, right? Because you always put a plus c when you take an antiderivative. And we looked at one specific example of this was the moving object example. If you're given acceleration, you can work your way backwards by taking two antiderivatives to get to the position function.